Artificial intelligence is changing literally everything right now. We're seeing it completely revolutionize healthcare, finance, manufacturing, cybersecurity, and even scientific research. But there's a hidden side to this whole revolution. AI has a massive physical footprint. Like, did you know that a single brief conversation with a large language model can consume essentially a half-liter bottle of fresh water just for data center cooling? Or that AI data centers are projected to consume as much power as an entire small country in just a few years? It's wild. Behind every single language model you use are these incredibly dense racks of GPUs, CPUs, memory modules, storage drives, high-speed networks, and of course, the immense power and liquid cooling infrastructure required to just keep the whole shebang running. So as these AI data centers keep growing at this unprecedented rate, we're staring down a very real, very pressing physical and environmental challenge.
Okay, let's dive right into this. Here's our roadmap for today's explainer. Number 1, the AI waste problem. 2, what is composable infrastructure? 3, real-world hyperscaler case studies. 4, the circular AI lifecycle. And finally, 5, making IT sustainable.
Section 1, the AI waste problem. Right, so to actually understand the solution, we first need to clearly define what's going wrong as our data centers expand. Because the physical hardware required to train and run these massive models, it's piling up and it's creating a colossal environmental footprint. Which really brings us to the central thesis of our explainer today. How do we scale AI without scaling waste? Well, one of the absolutely most promising answers to this is something called Composable Disaggregated Infrastructure, or CDI for short. Honestly, think of it like a giant box of Lego bricks for your computing hardware. Instead of buying these pre-glued sets that you can literally never change, you just snap the pieces together exactly as you need them. This Lego-like approach is rapidly becoming the architectural foundation for what we call green AI. So here's the main pain point we're dealing with. AI data centers are incredibly expensive, they're super power dense, and they are massively resource intensive. Imagine you've got this highly advanced, ultra expensive GPU. It's fully powered on, it's chewing through energy, but it's just sitting there, waiting for data. That's not just a performance bottleneck, right? It's a massive sustainability issue. If your memory is stranded inside one specific server, while another workload, literal right down the hall, desperately needs more memory, well, data centers are forced to buy more hardware than they actually need just to bridge that gap. And if storage can't feed those training jobs fast enough, those power-hungry GPUs, they just sit idle. Ultimately, over-provisioning your infrastructure wastes enormous amounts of energy, cooling, and money. It's a huge problem. Section 2. What is composable infrastructure? Now, what's really interesting about this is how it completely shifts our focus from the problem of waste directly to the mechanics of the solution. So how do we actually fix this? Look at the contrast here. Traditional infrastructure basically packages resources into these rigid, fixed servers. Every server comes with a locked-in amount of CPU, memory, storage, and networking. And sure, it's simple, but AI workloads are anything but simple. Training a brand new model requires massive GPU clusters working perfectly in tandem to churn through billions of parameters all at once. On the flip side, inference, which is really just asking the AI a question after it's been trained, might just need extreme memory efficiency to get you fast answers. Composable, disaggregated infrastructure? It completely flips this fixed paradigm on its head. It separates all these resources out into fluid pools, and then it uses software to dynamically assemble the exact right configuration for each specific workload, right on the fly. I love this quote because it brilliantly illustrates the paradigm shift. Instead of asking which fixed server is available right now, CDI asks, what specific resources does this AI workload actually need? This shift in mindset is fundamentally central to building sustainable AI infrastructure. It essentially means we only use exactly what we need, exactly when we need it, without over-ordering hardware just to play it safe. Section 3, hyperscaler case studies. Now, you might be wondering, okay, this all sounds amazing in theory, but is anyone actually doing it? The answer is a resounding yes. Let's look at some real-world proof. Because the major industry players are actively validating this architecture at a massive scale right now. Here we've got 3 incredible real-world examples. First up, Microsoft Azure's research on Pond. This is a memory pooling system based on CXL. Now, CXL is essentially a super-fast, next-generation connection standard that lets memory be shared directly across multiple servers. That directly eliminates that problem of stranded memory we just talked about. Then we have Meta's disaggregated scheduled fabric, or DSF for short. They're actually disaggregating networking hardware, things like line cards and fabric cards, which are basically the physical boards routing all the data, to overcome physical networking limits. And this ultimately delivers significantly more computation per watt during those massive AI training runs. And looking at it from a commercial standpoint, Liquid uses its Matrix software to provide a unified interface for dynamic GPU memory and storage pooling. It essentially allows servers to be composed in seconds. This makes sure that your existing assets are completely maxed out before you even think about buying new ones.
I really want to highlight this specific metric from Microsoft's Pond research. By testing across 158 different workloads, they found that pooling memory reduced their memory hardware cost by 7%. And they did this while keeping performance practically identical to traditional setups. Now, 7% might sound a little small at first glance, but you have to remember, when you're a hyperscaler buying literally billions of dollars in hardware, that is hundreds of millions of dollars saved. This proves that pooling isn't just a win for the environment, it is a highly efficient financial strategy.
Let's move beyond just the cloud and see how this builds out in enterprise and rack-scale systems. HPE is bringing this directly to the enterprise with Synergy and OneView. They are replacing dedicated hardware islands with those fluid resource pools we mentioned, which drastically reduces those costly silos. Meanwhile, NVIDIA is tackling this from a rack-scale perspective with their GB200 and GB300 NVL72 systems. By using topology-aware scheduling through their mission control plane, which basically means the system actually understands the physical layout of the hardware and places tasks along the absolute shortest, fastest physical paths, they ensure workloads are placed exactly where they need to be. This massively improves performance and totally eliminates idle time across high-density AI infrastructure. Section 4, the circular AI lifecycle. So now that we've seen the hyperscaler case studies, let's zoom out and look at what this means for the broader global picture, specifically when it comes to the e-waste stream. In a traditional setup, if a server runs out of memory, you often have to rip out and replace the entire server, even if the processor and the chassis are perfectly fine. CDI entirely replaces that wasteful full server refresh cycle with a modular upgrade model. Think about how this changes daily IT operations. First, we can extend the life of our parts simply by not trashing them prematurely. We can reuse components, like taking a perfectly good GPU from a retired server and just dropping it into a fluid resource pool. We can repurpose old training GPUs into inference GPUs. And finally, we only replace exactly what is actually broken or entirely obsolete. To really put this into perspective, the world currently generates over 60 million metric tons of electronic waste every single year. And data center hardware is a massive, highly toxic contributor to that pile. Let's break down the mechanics of how this circular life cycle actually reduces that tonnage. With CDI, you can expand memory completely independently. You can upgrade storage on its own. You can reassign those incredibly expensive GPUs to totally new tasks without doing full system replacements. By just keeping existing hardware in play longer, we drastically reduce the sheer volume of whole systems entering the electronic disposal stream. Section 5, making IT sustainable. And this brings us to the final conclusion of our explainer. It is time to tie this incredible technical architecture back to our ultimate goal, true sustainability. So the crucial point here is exactly this. Green AI is not only about sourcing cleaner energy to power our data centers, it is also about building smarter, much more adaptable infrastructure. True green AI requires us to use every single GPU, every memory module, every storage device, and every network link with absolute maximum efficiency. Because by doing so, we reduce waste, we lower our costs, and we build AI systems that are genuinely sustainable by design. The frameworks we've been discussing today are part of a much larger movement toward responsible technology. If you really want to dive deeper into how you can apply these architectures in your own data centers, I highly recommend picking up this book, Making IT Sustainable Techniques and Applications, published by Academic Press. The author, Mikhail Glukhovtsev, provides just an incredible comprehensive guide for anyone looking to really lead the transition to sustainable computing. As we wrap up this explainer, I want to leave you with a bit of a provocative thought. If your infrastructure isn't composable, how much of your next massive AI investment is just going straight into the landfill? Thank you so much for joining me for this explainer, and I challenge you to start thinking about how you can build smarter, not just bigger.